Okay, so this is, at the end of class last time, we were able to write this, the approximate accumulation function. And we first wrote that as a piecewise function, meaning every completed interval had to have its own rule. And we said if we have lots of intervals, that's really going to be inconvenient. So we want to write it in one line. And so we worked through all the nuts and bolts on Tuesday of being able to write this approximate accumulation function in one line. And here's the form of it. So what I'm showing you of that is the most important part. There are details in there that you have to know, but all those details cannot cloud your understanding of it like this, okay? Like this. So let's see what this is all about. This is all really primarily about two key principles that we've been talking about since the second day of class. All right, so we introduced this on the second day of class. Remember the smartphone? The difference between a change and an actual value of a variable and a change. So since that day, we really talked about these principles. The first is change in dependent is the constant rate times the change in independent, or dy equals mdx. Okay? This is the first really important kind of principle that's building this function. Where do we see that? So where do you see mdx being a little change in y? Where do we see that? Everywhere, okay? There it is. For every completed interval, we're calculating it as r of some independent value, right? So the output of the r function is the rate of change times change in x. So for every completed interval, we're using m times dx. And then what do? We sum those all up, right? And we sum all those individual completed intervals. We don't sum up the intervals. We sum up the change that we get from all the completed intervals. Where else do we see it? We also see it in the current interval. Same thing. M dx, rate times the change in x, okay? Where are we getting these rates? We're getting the rates from the approximate rate function, right? Which we got from the exact rate function. So we're using function notation to express these key rates of change that we're going to use to build up changes in y. And then multiplying it by the change in x. What's the other key principle? Final equals initial plus the change. Final equals initial plus the change. Worked on this since day 2, right? How do we see that here? Where's y initial? Well, y initial is like what's already been accumulated over all of the completed intervals. Right? So for some value of x, we have all the accumulation from all the completed intervals. And we can think of that like y initial. So that's the sum of all those little bits of accumulation. Plus, what's the change? So the change is the amount accumulating within the current interval. So we've got to think of x as a variable. X is increasing through these intervals. X is increasing through these intervals. And at any given kind of value of x, it's in a current interval, and so there's this. It's accumulating. You're getting accumulation in the current interval, and that's the r dx on the right there. So x, just think of x starting at a, and it's increasing through these intervals. And so then at any value of x, you have all the accumulation from the completed intervals, which we could say y initial. That's the sum. And then a little bit more for what's accumulating in the current interval. All right, so this is the key. These are the key principles behind this function. Okay. So now, what about the secondary things? So there's more to fill in the blanks, but we really first we want to see it like what we just talked about. That's first and foremost. Okay, but then these secondary nuts and bolts are important. The first one is number of completed intervals. So how many of those amounts of accumulation do we sum up? Well, as many as there are completed intervals, and that was that floor function we figured out last time. So that's the number of completed intervals. That's how many things in the sum we're going to be adding together. How many amounts of little bits of accumulation, each one found by m dx, right? Next thing was, what is the rate? What x value gives us the right rate for the jth interval, right? So for the jth interval, we need to go over a plus j minus 1 delta x. That gets us to the left side of the jth completed interval. So that's the rate we'll use as a constant rate for that whole interval. Okay? And the next thing was, left x is specifically the left side of the current interval, right? Left x is specifically the left side of the current interval, as opposed to the left side of any completed interval. Okay? So that's back there. This is the left side of a completed interval, specifically the jth completed interval. This is the left side of the current interval, right? That's the left side of the current interval, and then times dx. And we said we want to write dx in terms of x, so dx would be x minus left of x, the little amount of change that we have in the current interval. So that completes it. So big picture, most important. And then these other things are important. You have to know them, but don't let them confuse you, right? So make sure you got the big picture first, and then start building your understanding of the little pieces that we fill in. Any questions on the function? Okay, so let's work on a new context. And so you can get the sheet. Okay, so what am I showing here? I'm showing on the left side, so that the context is unloading sand onto a scale. Unloading sand onto a scale. On the left side is the rate of change of weight on the scale as a function of time. And that rate of change is in 100 pounds per second. 100 pounds per second. And the time is in seconds. So here's that. And what kind of function is this? What kind of function is this? Exact rate of change. Exact rate of change. Okay? And so we're gonna for this particular context, this worksheet is gonna take you through what we've been doing over the last 2 weeks. So work together, work efficiently. But let's go as far as, let's go through number 5. Work through number 5 and then stop. Don't start on number 6. We'll do that together. We'll start that together. So work through number 5. You got about 10 minutes. See if you can get through number 5. Okay, so I'm showing 1 through 3 now. I've got 1 through 3 up there. So one thing I noticed a lot of you overlooked was showing the values of the rates. Where would you show the values of the rates? The y-axis. The rate of change function, its dependent variable is rate of change. And you see values of the dependent variable on the y-axis. The points, the correspondence points, are simultaneous values of both variables. Okay? Those represent the location of the simultaneous values. So if you're just talking about y values, in this case using function notation, you're going to label those on the y-axis. So the rates, that's your rate scale on the y-axis. Okay, and then on your left graph, or your right graph, seconds, same independent variable for both. And then now we're going to be talking about accumulation, so of sand, or weight, accumulation of weight, so that the units will be 100 pounds. 100 pounds will be the units on the, whereas your rate units are 100 pounds per second. Okay? And whenever you look at a static graph, you have to think of it. There was some point in time when that thing was generated. X increased. And as X changed, the other variable changed. So in this case, rate of change. Okay, so now I'm showing how the approximate rate function would be generated as X changes. That has to be your image of graphs. Variables vary. Okay. Okay, how are the sketches coming on the approximate accumulation function? I see lots of good ones here in the front. So So the amount of the weight's going to go up, and then the weight's going to go back down, right? Lots of no's in the front. What's the weight going to do? Going to go up, and then it's going to still go up. This is the rate of change. So if the rate of change is positive always, then the amount of sand is always, the pounds is always increasing. So it's gonna go up. How at first? How's it gonna go up at first? It's the very first. Slow. And then at around 1.5 seconds, it's gonna be coming out the fastest, right? The weight's gonna be increasing the fastest, and then towards 2.5 seconds, slow. So does that make sense with how the weight might increase as it comes out of the truck, right? So a little bit at first, and then most of it, and then there'll just be a little bit at the end, just residual, right? Okay, so I saw lots of good graphs in front. So here we go. So here's that corresponding accumulation function. Is it a curve? Is it a curve? Why is it not a curve? It's a lot of linear pieces. Why? Because we have constant rate. We're building that on constant rate of change, right? Every one of those intervals, we're assuming a constant rate. Those blue constant rates means what for accumulation? It means linear, right? It's going to be linear. Okay, so any questions? That's 1 through 4. Questions on 1 through 4? All right, number 5. What's the first type of function in this? It's on its exam. This is on the exam. This exact question, number 5 on this worksheet, is on the exam. All right, what is the first kind of function that we have that we're in this process? Exact rate of change, the red one. And from the exact rate of change, we build the approximate rate of change using the left side of every interval, right? The actual rate at the left side of every interval to be the constant rate in our approximate rate function. Next, from that we do approximate net accumulation. Good, approximate net accumulation. All right, and that's what you sketched, and I'm showing here on the right. Approximate net accumulation. Okay, and the final is exact. So we can say exact net accumulation. Okay, but the key is exact accumulation. Exact from approximate accumulation to exact, whether that's net or total accumulation. Okay. That we'll talk about today. Okay, but we still we want to do some more with this. We want to understand how this formula works, right? So the formula that we derived on Tuesday and then reviewed here at the beginning of class, we're going to look at specifically does that show up? Great. So let's look at 1.4 seconds. At 1.4 seconds, how does the accumulation function correctly calculate A of 1.4? So first of all, what is A of 1.4? How would you define A of 1.4? What is that? Okay, so I have the total accumulation at 1.4 seconds. First of all, is it total or net? Net. So our A function is always a net accumulation. Okay, always starting from 0, right? It's the amount of change. It's the amount of change. Okay, and then there's one more detail we need here, right? So it's the net accumulation. What specifically? Okay, yeah, that's true. That's where it comes from. But it's the net approximate accumulation. It's based on those constant rates, right? It's based on the approximate rate function. So A of 1.4 is the approximate net accumulation of pounds of sand at 1.4 seconds. So let's estimate that value. Stop this here. And then we're going to see how the A function computes it. So 1.4 is right here. So let's eyeball it from the graph first. eyeballing that from the graph. About what? About how many pounds of sand at 1.4 seconds? Yeah, maybe a little bit more than 350. It looks like 355 or 360 or something like that. We'll say 355. Okay, so now we're gonna in the bottom of this worksheet we're getting the nuts and bolts of how does A work to actually calculate the approximate value of the net accumulation of pounds of sand at 1.4 seconds. Okay, so first of all, let's look at, we're on number 6. Look at, so here we are at 1.4. What is left of x right now when A is 1.4? We're pausing life here at x equals 1.4. What is left of x? Some people are saying 1.2. What do you think? Not that. That. He's on the same. Okay, so let's see if I can do this here. All right, there we go. I just don't have room for both. Let's just toggle back and forth. Okay. So is it 1.2 left of at 1.4? Right. It's the x value at the beginning of that current interval, which is 1.2. Should make sense. Okay. So then what is the value of dx? What's the value of dx currently when x is 1.4? So remember, dx is the amount of change in the current interval. How much change have we seen in the current interval? 0.2, right? 0.2, or this, right? Or x minus left of x, right there. That's it. That's the value of dx. So it's 0.2. 1.4 minus 1.2. Okay. When x is 1.4, how many completed intervals do we have, right? So it's always about, we've gone through some number of completed intervals, and we're in a current interval. How many completed intervals? No formulas. No formulas. Idea. 4 completed intervals, right? There's 4 completed intervals. You see it. Here's the constant rate for the first, constant rate for the second, third. We're in the which interval? 5th. Okay. So J in the summation is going to go from what to what? It's going to go to what? When we're in the 5th interval, J is going to cycle 1, 2, 3, and 4, right? It's going to cycle through the so it's going to be, so let's put a 1 here. 1, 2, 3, and 4. Okay? So J is going to cycle through 1, 2, 3, and 4. Okay? When J is 1, so now this is for the completed intervals, right? So this is for the completed intervals. When J is 1, what is our value of A, first of all? That's 0. We're starting at x time equals 0, so that's just going to be 0. And then J is 1, so then we get 0 plus 0. So the input, the x value, so what is this? This is the x value at the left side. That's that formula for the x value at the left side of the jth completed interval. So in the first completed interval, that left side of that first completed interval is 0. Okay, and so then we're going to have r of 0. Is the rate there? For that, that's going to be the constant rate. And then this will be r of 0 times, what is our delta x? 0.3. Okay, so let's pick off. Can you estimate r sub 0 from the graph? Estimate the value of r sub 0. What is it? Estimate. 0.25, someone said? Okay, so then when we take 0.25, that's the constant rate we're using, and then we're going to do that for change in x of 0.3 to get the change in y. What do? Multiply together, right? So we're going to multiply those together. And we're going to get what? 0.3 times 0.25. Is that 0.075? What does that number mean? 0.075. Exact or approximate? Approximate amount of accumulation for the first completed interval, right? Rate times change in x. So this is how that formula is doing it, right? So those three things we just did are this part of the formula, right? For the first interval. We found the x value, which was 0. We took r of 0, which was 0.25, and multiplied it by 0.3. Then what does it do? It goes on to the second interval. So now j is 2. And we're going to have a plus 1 delta x, right? When j is 2, a plus 1 delta x equals 0.3, right? So 0 plus 1. So in the second interval, we're going to go across one interval. So we'll get to 0.3. The rate that we're going to use then is r of that. Approximately what? Someone said 1. I'll go with it. All right, and so therefore, the amount of accumulation in the second interval is rate times change in x. Right here, rate times change in x, which is about 0.3, right? 0.3 times the 0.3 equals okay. So let's just decide on what these approximate rates are, and I'll let you do those two. We'll just keep going together. Here we go. So when j equals 3, that's the third completed interval. That formula gives us the x value, right? X value at the left side of that third completed interval would be 0 plus 2 times delta x, which is 0.6. Then you take that left value, plug it into r, r of 0.6 from the graph approximately. I heard 4.75. So I'm hearing about 2.8. Is that agreeable to everybody? And then we're going to take, what? R of 0.6, which is 2.8, times the change in x. And what does that give? So 2.8 times 0.3. 0.84. What? That's the amount of accumulation in the third completed interval. Calculated by this little formula right here, right? When j equals 3. Fourth interval. The x value will be 0.9. We approximate r of 0.9 as 4.75. We're going to take that 4.75, right? R times delta x. So take 4.75 times 0.3. As soon as you get it, tell me. 425? Someone else get that? Yes. Sweet. Okay. What's that? That's the amount of accumulation in the fourth completed interval. Again, calculated by this when j equals 4. What's left? Partial interval, right? Partial interval will be r of left of x, which will be r of 1.2. So partial interval, this is the partial interval, right? R of left of x. What's left of x? We said is 1.2, so we need r of 1.2 times dx, which you said was 0.2. Approximate for r of 1.2. From the graph, what is r of 1.2 about? Quick. 4.25. Someone else agree with that? Times 0.2. Is that 0.85? Okay, so accumulation from each of the 4 completed intervals, computed by the sum, right? J equals 1, J equals 2, boom. J equals 3, boom. J equals 4, boom. And then the little more accumulation from the partial interval. R of left times dx, 0.85. What are we going to do? What are we going to do with all those? Add them, right? We're accumulating. A little bit from the first interval, a little bit for the second. Going to add them up, and we expect to get. What do we estimate? 255 pounds, right? 355? 355. Okay, add those 5 numbers up. Because that's what this does, right? Sums up the 4 completed intervals plus the little bit from the 3 point what? 49? So she said 3.5. I said 3.55. She was closer. But these were also, with all those rates, we pulled off the graph. So those are going to affect our estimations from the y-axis, right? But there we go. 300, our estimation for what? Accumulated of pounds at 1.4 seconds, 349 pounds. So that's how the A function does that. But then x is increasing, right? So for any value x, it's doing this. It's keeping track of all the accumulation from completed intervals, and then giving us a varying amount of accumulation through the current interval. So it's always adding on as x increases. So we just paused time and we calculated one of them. But A of x gets them all for every moment, right? It gets the approximate accumulation for every moment as x increases through all those intervals. Questions on that? Understanding how it does it. So the whole point of filling all this in was to see what does that formula do to calculate this number, 349 pounds. So go back and review that. How is it doing that? Any questions? Okay, so now let's look at let's look at the graph of the approximate accumulation and do some thinking about that. Can I erase this? So now I'm going to show you some visuals. It's not happy. Okay, so here's the same situation, and I'm showing the formula up there for the approximate accumulation function. Pick a number between 1 and 4. He wants 3 first. Here we go. So I'm highlighting with red bars and question marks quantities that relate to this function. You're to figure out what quantities. So there's 2. There's a question mark for the horizontal bar and a question mark for the vertical bar. What expressions, partial expressions from the AX formula is represented by each of those? Think and then talk. So what part or parts of that formula is the horizontal red bar and the vertical red bar? Okay, horizontal bar. Horizontal bar. What's the length of that? for any given x value, what's the length of the horizontal bar? What do you think? X minus left of x. It's x. Delta x. Is it delta x? Is delta x a variable or a parameter? It's fixed, right? Is this fixed? No. And which interval is it showing? This is about the current interval, right? How much have we gone into the current interval? What is that? Which shorter is? You're right. You're absolutely right. dx. The horizontal one is dx. It's how much we've gone into the current interval. dx. Okay? What part of that expression is the vertical? Okay, yeah, so it's the amount of accumulation due to the current interval. It's the amount of accumulation due to the current interval, so it's, the vertical is this. If that's what you said, you got it. It's the amount of accumulation due to the current interval, which is increasing as we increase through the current interval, right? Questions on that? Really important that you can see this. Okay, give me another number between 1 and 4. 2. He wants 2. Here we go. I got more question marks. So there's the horizontal question mark, and that's like the x-coordinate of the point. So this is kind of redundant, right? So there's the ordered pair is redundant of the 2 question marks on the axes. So you're answering 2 questions here. Horizontal question mark, vertical question mark. Those would be repeated as the coordinates of that point. Does it make sense? So you're answering 2 questions. Go. Okay, horizontal. Horizontal, how would you describe, somebody new, how would you describe the horizontal? Somebody new. Somebody new. Yes, ma'am. Delta x. It's always showing the length of delta x. Is that right? It's more than, it's bigger, right? It's bigger than delta x. Yes, sir.
Total elapsed time of all completed intervals.
Total elapsed time of all the completed intervals. What do you think? Yeah, this is the change in x for all the completed intervals. How would we express that? So how could we express that? That's not really anywhere here, but how could we express the total change in x for all the completed intervals? So the number of intervals, right? The number of intervals, so it'd be this thing, the number of intervals times what? Times delta x. So this expression, so this I'm deviating, but the number of completed intervals times delta x will give us that change in x for all the completed intervals. So yeah, here a is 0. So if a wasn't 0, then it would depend how I frame that question mark. If I framed it back from 0, then you would add a. If I framed it starting at the, yeah, it would depend. But here we wouldn't need to. Okay, what about vertically? Vertically, what part of the equation gives us the vertical question mark? So it's complete, it has to do with complete interval, so something to do with this over here. So what part of this over here is the vertical? The whole thing. The whole thing. It's the sum of the accumulation from all the completed intervals. That would be the vertical quantity with the vertical question mark, right? It's the sum of all the accumulation from the completed intervals. And that's what I'm showing vertically. Okay, let's do this one. There we go. Okay, what is the vertical? What is the horizontal? Go. What's the vertical? What's the horizontal? Okay, hopefully this is easier. What's the horizontal? X. Just X. What's the vertical? A of X, or the entire right-hand side. X and A of X, or the entire right-hand side. Last one. Okay, so I'm just talking about here. One of those question marks. So they're all examples of what? So just one of those question marks represents what? Think and talk. Just one of those question marks represents what? They're all examples of the same thing. And what part of the equation would you circle? What would you circle in the equation to represent one question mark? Okay. So, does it have to do with completed intervals or partial interval? Completed. What is it about the completed intervals? One of those question marks represents what about the completed intervals? Yes, sir. Yeah, so it's accumulation due to one completed interval. Each one, so the first one is that's the accumulation from the first. J equals 1. There's the accumulation when J equals 2. That's the accumulation from the third interval, J equals 3. And then the accumulation when J equals 4. So what would you circle for one of those question marks? What would you circle in the equation? Right? Do you mean right? Yeah, the left side without sigma, right? So it'd be this. The accumulation from one interval is right there. One complete interval. From one complete interval. So each one of those question marks is that which I circled. For each J is going to give you a different one, right? Each J gives you a different one. Okay, so now we've come to the time when we want to take this to the next level here, to the fourth function, which we know is what? Exact accumulation. So let's talk about how would the exact accumulation compare in this function to the approximate. So looking at our approximate rate, is the approximate rate too high or too low? Too low. Now it's too high. Okay, so by the time it gets to the maximum rate, our accumulation is going to be, our approximate accumulation, is it approximate is too high or too low? Too high. Okay? And then after that, the rate is too high, so then it's gonna catch back up, right? It's gonna catch back up. It won't be too low. It's gonna go back to being right. Okay? So what will the exact accumulation function look like? kind of like the approximate, well, so not further left, but further up, right? So it's going to be above, it's going to be up from that because we're estimating too low at the beginning and then it has to catch up at the end, right? We're estimating too low at the beginning and then, but towards the end, it will catch back up because it's too high in the second half. So what's going to be the key to getting from this approximate accumulation function to the exact? What's going to be the key? So making a smaller interval does what to the approximate rate function? Yeah, so it makes it. So now that I made R 0.258, 2578. And you see what happens. That approximate accumulation function just moved up closer to the actual accumulation. So when you make a better even smaller intervals, right? So smaller intervals means that the approximate rate function does a better job approximating the real rate function. And therefore the approximate accumulation function does a better job of converging on this mysterious exact accumulation function that we imagine, right? We imagine that exists. And we can get closer and closer to it with smaller intervals. So here's really small, 0.0, basically 0.03. And what do you notice about that approximate rate function? Besides it's going really slow. Yeah, it's like if you're sitting in the back, you might not be able to see that as approximate, right? It looks just like the old one, but if I zoom in on that, it's still a bunch of little constant rates. It's still a bunch of little constant rates. So what we say is we're going to just make those intervals small enough so that we can't tell the difference between exact and approximate. So let's just make them really small. So like 0.005. So I'm still showing the approximate rate function just for a very, very small interval, 0.005. And so we can't really tell the difference between the approximate rate and exact rate. And likewise, we can't really tell the difference between approximate accumulation and exact accumulation. GC's working hard because of all those little tiny constant rates. Okay? And my computer has too many applications open. Okay? All right? So this is the idea of getting to approximate accumulation. We'll make those intervals smaller and smaller. Don't back up. We'll make those intervals smaller and smaller until we can't tell the difference. Until we can't tell the difference. And then if we can't tell the difference, indistinguishable, then we've converged to exact accumulation. And then when we do that, we don't want to have this big cumbersome equation anymore. So we want to talk about what do we have? What new notation do we have for the approximate accumulation function when delta x is super, super small? And we've essentially converged on the exact accumulation. So let's do that slide and we'll be done. Here we go. So the approximate net accumulation function is this. How are we going to represent the exact net accumulation function? How are we going to approximate the exact, or not approximate, how are we going to write the exact net accumulation function? Meaning, how do we want to change our notation for this thing when delta x is super, super small? And we essentially have exact accumulation. It's what's called an integral. An integral, all right? This thing, integral, the things they never taught you before. This is the same as this, but with a super small delta x. And that's a lot easier to write. But what we want to see is that in that notation there, this integral notation, we have essentially the same kind of idea. Where do we see the same thing? Well, this is Greek sigma, which stands for what? Sum. This is German S, which also stands for sum. Okay? So we got Greek sigma, becomes German S. And then what is it we're summing up? Can you see it? What are we summing up? Rate times small change, right? Rate times small change. So there it is. That's our constant rate of change, right? But now the delta x's are so small that it's like we're taking every single rate, right? We're taking like it's the function, right? So we're continuously taking every single rate. And then times our very, very small change in x. So it's still the sum of accumulation of y. Which is dy. M dx, right? So there it is. M, the rate, times dx is our dy, and we're going to sum all those up. So this integral notation is the same thing as our long form approximate accumulation function, but when delta x is super small. Okay, next week we'll put up the resources for studying this weekend.